Hello friends, welcome to Abaqus Acumen for quick and sound learning. So in this video tutorial I am going to explain you about the quasi-static analysis of this side door beam, and this side door beam is nothing but a hollow steel pipe which is subjected to quasi-static loading with this rigid cylinder, and this is displaced by 100 millimeter in this direction. Typically this quasi-static test has been conducted at lab level for this side door beam. This is evaluated, the performance is evaluated in terms of the load offset deflection results, wherein it is expected to deform, and while deforming it also should have ability to absorb the impact energy. This simulation is carried out in slow rate of application condition, and that is a quasi-static condition wherein the inertia effect will be negligible or should be zero. And when you say this, the kinetic energy of this simulation will be less or tending to zero. So let's go back and understand some background of about this tutorial. So this is a fancy car what you see on your screen, that is a BMW car. And although in these modern cars there are several advanced electronic systems for the as a safety features, but still a passive safety is one of the critical part or critical areas for this safe vehicle design. And when we say the passive safety, so this is the side door intrusion beam, which is one of the key component for this safety, that is a side impact safety for the vehicles. And this is typically arranged inside this side door assembly, and the main role of this side door beam is to protect the occupant from the hip injury or any side door intrusion or side impact intrusion. And it should have optimum stiffness, so when it deforms it is expected that it should absorb the energy too. And then this side door beams are evaluated for its stiffness under the quasi-static, that is a slow load application in lab test. So we are simulating this performance evaluation of this side door beam under the quasi-static condition, which will mimic the slower load application for this door beam evaluation. So this is a problem definition of quasi-static tutorial what we are going to discuss today. And this is the construction of the FEM model. We have this hollow pipe, that is a beam which is fixed at these two ends, and this beam is applied with prescribed displacement of 100 millimeter in the negative x direction, and the beam length is around 1000 millimeter, that is 1 meter, and the diameter is 40 millimeter, and the thickness is 3 millimeter. And the rigid cylinder, the diameter is 300 millimeter, and the width is 60 millimeter. The material for this beam is steel, and the material is defined in Abaqus as a bilinear sustained curve. So these are the properties what we'll be using when we define the Abaqus material, that is steel material. And the loads and boundary condition, as discussed, the circular beam is fixed at ends, and the beam is deformed by rigid cylinder with the 100 millimeter displacement. Okay, when we set up this model, first step we need to understand the time of load application. So that here, as I mentioned, the prerequisite for the quasi-static simulation is we need to apply the load in a slow rate, and there should not be any inertia effect, and as well as the kinetic energy when we do this simulation has to be minimum. So decide on the load time. We need to first extract the frequency of this beam structure, and based on the first frequency we need to understand what is the time of load application. So once we decide on the time, we need to do a input deck setup for this simulation with in the dynamic explicit domain, end time as a first frequency based on the first frequency. So unit system what we would be using for this tutorial is Newton, millimeter, second, and ton. This is in general what we use in almost all the tutorials for in Abaqus Acumen. So before we go on to the next step, let me make you aware about the possible pitfalls which you can go wrong. So one of the possibility that if you apply this displacement, that is a prescribed displacement of 100 millimeter with the end time of say 2 e raised to minus 4 second, that is in a very short time, you may end up having the deformed shape which is the as same as the semicircular shape of this rigid cylinder, and this is a very localized effect, and the impact speed or the push speed would be around 400 meter per second, which is too high when we talk about the quasi-static slow rate application. And when we look at the energy balance for this kind of simulation, you see this is a kinetic energy curve which is way above the internal energy, and this simulation is mostly governed by the kinetic energy part. When we compare to the slow rate lab test results, it will be a total deviation from the reality. Similarly, if you look at the reaction forces, which is very high at the time of impact, and it is just goes down. So overall, this kind of possible errors you need to take care to avoid all this wrong way of simulating quasi-static condition. So we have come up with rather this is the tutorial. It shows about how to decide this end time based on the frequency and then set up the deck in explicit solver. As I mentioned, the dominant response of quasi-static analysis will be the first structural mode for this beam kind of a structure. So this is in the background. I already conducted the modal analysis, that is the frequency analysis, and extracted the frequency for this condition of fixed beam. And as a first step, or the first mode, is the most dominant node, which is a bending mode, and the frequency is around 248 hertz. So based on this frequency, I have calculated the time, that is simply it is reciprocal of frequency, that is 0.004 seconds. So end time, what we know now is 0.004 seconds. So based on this end time, we can calculate what is the speed of load application, that is the distance, that is we are going to push the rigid cylinder by 100 millimeter, that is 0.1 meter, divided by this end time. The velocity what we will be using is around 25 meter per second. So let's go back and see whether this number of 25 meter per second is viable when we talk about the quasi-static condition. So here is the one tip or the one guideline mentioned in this tutorial is calculate the impact velocity by using the formula which we did, and that is 25 meter per second. And a general recommendation is to limit the impact velocity to less than 1%. Okay, and so why so is the typical wave speed in metal is 5000 meter per second. Okay, so we need to understand the wave speed of the material, and it should be less than 1% of wave speed of the material, so that is 5000 meter per second. So when we say 1% of this 5000 meter per second, which is around 50 meter per second, and based on this we can safely say that it is less than 1% of this number. So we can go ahead and simulate this analysis using this impact velocity or the push velocity of 25 meter per second. So in the end, when we do a FE model setup, we will be applying the prescribed displacement, that is a displacement to the cylinder with the end time of 0.004 millisecond. So that will be the two parameter what we'll be taking out. So just for your understanding, so what we'll be using in the model, FE model, that is a time, that is end time 4 seconds, and then we'll be using the prescribed displacement or the boundary displacement of 100 millimeter, that is 0.1 meter. With all this previous exercise of ensuring the velocity, that is the push velocity of 25 meter per second, is just for our cross checking, so that our analysis is accurate and reliable. So we'll be using these two inputs from this exercise. That is the first step of doing the frequency analysis. Okay, so let's move on to the next step, that is, so once we do this build up in the FE model build up in AbaqusCAE, so we will be interested to look at the animation or the deformation pattern of this beam. So this how it would look like, and then the reaction force we need to understand. So this is the nature of reaction force what we will get, and then of course we need to counter check the energy balance curves. So this is the kinetic energy curve, which is it starts slowly and then it stabilizes over the time, and the internal energy of this beam is continuously increasing. So this gives a snapshot like this satisfies the quasi-static condition, and it also relates well to the lab level test of slow rate load application. Okay, so let's go to the Abaqus CAE tool and build this FE model quickly. The first step is to build the beam. So it's 1 meter length, that is 1000 millimeter. Extrude this. So this is done. So let's go ahead and define the property as well. So this is steel, okay, and we'll be using the elastic part. Young's modulus is 2.1 e raised to 5, 0.28 as a Poisson's ratio. Okay, and what we'll be using is density 7.8 e raised to minus 9 tons per millimeter cube. So the plastic, it is a bilinear curve we'll be defining. 250 MPa is the yield stress, 0.0, and the second one we are considering 420 to 0.23 is a plastic strain. Okay, so this is a bilinear elastic plastic curve we are defined with this, or this is a plastic curve properties. So this is done, and then we will create a section property, that is shell. Alright, continue, and we'll be using the thickness of 3 millimeter steel. Let's assign this to this geometry. This is done. Let's go to another part, creation, that is a rigid cylinder. So we'll be drawing the circle and then we'll be extruding it by 60 millimeter. So let's draw the circle, which is 150 millimeter diameter. So sorry, 300 millimeter as diameter. So it's 150 millimeter is the radius of this circle, which is quite big actually. And then we need to extrude this by 60 millimeter. Okay, this is done. So as this is a rigid part, we need to define a reference node. Okay, so we can define this as a reference node. So this is done, and now we'll move to the assembly part. Okay, so let's do some positioning of the circular cylinder. So we need to rotate this part instance. In x-axis 90 degrees. Okay, and then we need to bring this at the center, so we need to translate this in G direction, positive G direction 500 millimeter, so that will bring it to center. Let me see, yeah, it's fine. And again, so it's around in positive X direction, so 150 plus 20, 170, 174, 174 with a gap of 3 to 4 millimeter is a gap. Oh, sorry, I missed the one point, so let's do it again. Okay, this is ready. Let's go to step, and here we'll be defining the dynamic explicit part, and we know the end time, that is 0.004 seconds. Say OK, dismiss. Let's have interaction. So we can create surfaces for these two part, so that is straightforward for us. So let's say create one is a surface. Surface one is say the beam surface for this beam. So we'll be selecting that is brown, and then there is one more surface we'll create, that is a rigid surface, that is a master. So we'll be using this, we'll be using the brown again. So and now we'll define the interaction. Interaction surface to surface. So we'll choose the first surface, beam surface continues, and then we'll choose the rigid one, and we'll define the friction. This process is something very familiar, what we have been using for several other Abaqus Acumen tutorials. Yes, children, alright. So we have defined the contact. So now we need to define, so we need to mesh it. So let's mesh this part, that is the beam part. So I will activate only the beam instance. Okay, this I will hide it. Okay, edges, we need to make this independent, alright. So edges, this card, this is okay. So we'll use around 5 millimeter as a element size. Done. So let's make this part. Okay, this is done. Let's go to the loads part. let me bring into a right view for the selection, not this one. Yep, this is good. Let me define the boundary conditions. So we need to fix the ends. So before that, we can do one more exercise. We can create a node set for this edges. So that will be easy way of doing it, because usually what happens if I select edges, so there are chances like you end up selecting the entire geometry and you constrain the entire geometry, then things will go wrong. To just avoid that possibility, the good practice is we can create a node set for this end edges. Okay, here we go, create nodes. I say edge 1, that is for boundary condition. Continue. So just zoom this part. Alright, oh, sorry. So you can select it now. Done. So now the other edge, create the set node edge BC2. Done. Okay, now we can define the boundary conditions. Create BC1. Yeah, so we need to fix this is edge 1. Wait, when cluster this. Okay, and there is one more, the other edge to continue and cluster this. It's done. So let's apply the displacement, that is forced displacement or prescribed displacement, to the rigid cylinder. Let's go to assembly, show. Yep, so we'll be applying the displacement in negative x direction. So before that, we need to constrain all the other degrees of freedom for this rigid cylinder. So we'll only allow the translation x for the rigid cylinder. So we can select RP and say done. We'll allow only x and rest of the degrees of freedom, that is dOF is 0. And now we'll apply the displacement. Okay, that is U1. So here I will put minus 1.0 and I will apply with the amplitude. Continue. So this is 0.0, amplitude is also 0.0. that is the first one. The second one is, we know the time 0.004 seconds, the amplitude is 100 millimeter. Okay, so this is a negative x direction, 100 millimeter. Alright, just say okay and select this amplitude. Okay, so we apply. So let me first hide this. Okay, and now we will only display the rigid cylinder. Now let's mesh it. Done. data sign. Okay, this is make it independent. All right. Okay, so this is done. Let's submit the job. So guys, what we have done is we created property assembly, and then we positioned the model properly, and then we defined the explicit dynamic time domain, then followed by the contact, then we mesh the part and load, and then we applied the load boundary conditions with the node sets node for the beam, and then applied the displacement to the reference point of the rigid cylinder, and then we mesh the rigid cylinder part as well. It is, we can set this tutorial for job run. We got the result for this model. You can see the animation, the deformation shape looks very nice, and this is being done as per the expected. And let's see the other results, like the history output, that is the energy balance. So this is the first parameter check we need to look for, that is internal energy and kinetic energy of the model. So that's fantastico. So we have the required energy curves are as per expected. There is an initial ramp in the kinetic energy, then it goes down and it becomes stable, and the internal energy curve, that is the red curve, which is continuously it is going or increasing over the time. So this is a good results what we got. And let's understand some field output as well. So we can look for the reaction force for the rigid cylinder. So this is for the reference point we can look for. So let's say plot. So alright, so this is the reaction force we got. We get some initial reaction force, and there is a deformation, then again it picks up. So this is the reaction force what we get from this simulation. So guys, this is what I wanted to show in this tutorial. And as I mentioned, in Quasistatic, that is a slow rate application, so we have cross verified the energy balance curves. The kinetic energy is low and it is stable over the time of application, and the time of application we also found it from the frequency, that is the first frequency. And we have set all this model, and you can try out few more iterations, like changing the time, that is total time, even further, increasing some 0.004 to some more number, and see what happens, what are the results. So in my view, if you increase this load application time further more, I mean from 0.004 to maybe 1 second, or sorry, 0.5 second, you can have more stable results. So this kind of iterations you can carry out, and make sure that your runtime is remain less and still you get the quality results. So that's the whole objective of the further iterations. Guys, I think you can view this tutorial time and again and practice this on your own, and you should be able to get this results once you follow this tutorial step by step. And I wish you good luck. And if you like this video, please go ahead and subscribe Abaqus Acumen, and also like this video. See you again. Thanks. Bye bye.